Have you ever wondered if a system could teach itself to get smarter? I don't just mean learning new facts, but actually fundamentally changing how it learns in the first place. Well, that's the wild idea behind something called network reification, and we're going to break down exactly how it works.
So that's really the big question we're tackling, right? How can a system move beyond just, following its programming and actually start to rewrite its own rule book as it goes?
Okay, to get our heads around this, let's think about it like this. Imagine a robot on an assembly line. But this robot doesn't just build cars. It's also watching itself work, spotting its own mistakes or inefficiencies, and then, get this, it redesigns its own gears and circuits to do the job better next time. That's the kind of self-improvement we're talking about. So what is network reification exactly? Well, at its heart, it's about taking all the hidden, complex rules a system uses for learning and making them explicit. It's kind of like popping the hood on a machine. But instead of a confusing mess of wires, you find a control panel that the machine itself can use to tweak its own performance. All right, here's the more formal definition. Network reification is basically a process. You take a network and you extend it by adding some new parts. But these new parts aren't just random additions, they have a very, very specific job to do. And this is the part that's absolutely crucial. These explicit states, their entire purpose is to represent the network's own structure. You're literally giving the system a mirror so it can look at itself, understand how it's built, and then figure out how to change. But how do you actually do that? I mean, how do you take something abstract like network structure and turn it into a real, tangible part of the system that it can then modify? Well, it happens in 3 key stages. First, you create that mirror we talked about. You add those new states that represent the network's own blueprint. Second, any changes or adaptations aren't some mysterious external process anymore. They're modeled as activity happening within these new states. And the end result? You get what's called a declarative model, a system where the rules for how it changes are totally transparent and actually part of the system itself. And this really shows the difference perfectly. A traditional or procedural model is basically a black box. Something changes, but you don't really know why. Some external algorithm just told it to. But a reified declarative model is transparent. The rules are internal. You can actually watch it think about how it's going to improve itself. Okay, hang on, because this is where things get really cool. We're not just talking about a system that can learn. We're talking about a system that can learn how to learn better. This is something called higher order adaptation. So at level 1, you've got your basic adaptation. Think of a spam filter. It sees new types of junk mail, and it learns to block them. It's learning, for sure, but it's pretty straightforward. But what if that spam filter could do more? What if it could look at its own learning strategy and say, my current approach isn't very efficient. I'm going to change how I identify junk mail from now on. That's level 2. The system isn't just learning anymore. It's learning how to learn. This second-order adaptation is pretty much metacognition for a network. It's the system thinking about its own thinking process. And to pull this off, you just do the reification process all over again. You build a new layer that observes and modifies the first learning layer. So if one level of this process gives us adaptation, and a second level gives us learning how to learn, is there a limit? Well, for a lot of really complex systems, it turns out that 3 seems to be the magic number of layers. And why 3? Because a 3-level model creates a completely self-regulating system. You have the base level that's actually doing the work, you have a second level that's adapting how that work gets done, and you have a third level that's controlling the whole adaptation process. It all becomes one single integrated architecture for intelligent change. Okay, so this is all really fascinating theory, but so what? Where does this actually get used? Well, this whole framework is giving us powerful new ways to model some of the most complex systems we know of, our own minds and the social groups we're a part of. The implications here are pretty huge. In cognitive science, this approach can help model how we learn, and it even gives us a way to think about self-awareness. And in the social sciences, it can help explain how groups of people change and evolve over time, based on things like our natural tendency to connect with people who are similar to us. So let's zoom out. What's the big takeaway from all this? What could this mean for the future of intelligence, both artificial and maybe even our own? Ultimately, network reification is a blueprint for building self-reflection directly into our complex systems. It's a huge shift away from just programming systems from the outside in, and toward creating systems that can understand and improve themselves from the inside out. And that leaves us with a pretty profound question to think about. As we build models in AI that can not only learn, but can understand and change their own learning, we're not just creating better tools. We might be fundamentally changing what it means to be intelligent. What do you think that future is going to look like?